Hey, welcome back to linear algebra. We're going to finish up our work in section 6.2, talking about something called orthogonal complements, an important construction. So we'll take an inner product space, as usual. We're assuming it's a finite dimensional inner product space called V, and then we'll take any non-empty subset of V called S. So the main definition, what I want to tell you about the orthogonal complement of that set S, it's just the set of vectors in V, so those x and v, that are orthogonal to every element of S. So you gather up those x's in V such that the inner product of x and y is 0 for every y in S. That's denoted by this symbol S with the perpendicular symbol, and we'll read it out loud as S perp. So S perp is the orthogonal complement of S. It consists of those vectors that are orthogonal to S. I'm going to leave it as an exercise to you that if S is any non-empty subset, it can even be a subset, it doesn't have to be a subspace, S perp is always a subspace. Okay, so that's going to be one of your exercises. You've seen constructions like this before. If you take a non-zero vector in R3, say, for example, and you let S, say, be the line through it, so you can visualize it in my picture here. I've got V drawn, some non-zero vector, that black arrow. S is the set of all scalar multiples of V, so it's the line through there. Well, then S perp is just the plane that's orthogonal to that vector, like you constructed. It was a common way to write down equations of planes in Calc 3. Is the V there is the normal vector to the plane. In general, we'll see at the end of this lecture that the orthogonal complement to the line through a given non-zero vector, it's always an n minus 1 dimensional subspace. So in R3, 3 minus 1 is 2, so you end up getting a plane. A couple more exercises for you. I'm going to randomly list them here. That the perpendicular space of the zero subspace is V itself. Okay, so if you look at the vectors that are orthogonal to the zero vector, you get everything. And if you're looking for vectors that are orthogonal to everything, only the zero vector does that. So zero perp is V and V perp is 0. I'll leave those are good exercises for you to get used to this definition. So we got two theorems to prove here in this section. The first one, theorem 6.6, says that if we take a finite dimensional subspace of an inner product space V, so we're going to let it be called W, it's a finite dimensional subspace of V, V has an inner product, and then you pick any element in V, you can always write that element as a sum, U plus Z, where the first term in the sum comes from W and the second term comes from W perp. Okay, and then moreover, if you take an orthonormal basis for the subspace W, there's an explicit formula for how to find that vector U. You just take the inner product of Y with VI for every I, making those the coefficients. They look like Fourier coefficients of the vector VI itself. Okay, so this theorem says that you can write any vector in V as the sum of a vector in U plus a vector in U perp. So in terms of a physics application, this is kind of decomposing the force vector y into two forces that are orthogonal to each other. It's a very common and useful construction in many physics applications. So this theorem is just saying that that kind of familiar construction is valid in any space in which you have an inner product. Okay, well, let's take a look at the proof. Let's give ourselves W a subspace. It's a subspace of an inner product space, so it has a basis, and we can use the Gram-Schmidt process to orthonormalize that basis. So we'll just assume that beta is an orthonormal basis for W. W has dimension k in my notation. And then given a vector y, I'm just going to define U by that formula in the theorem. So that makes the formula true. I could certainly write that formula down. Okay, so and then why would U be in W where all the VIs are in W and W is a subspace? So it's closed under scalar multiplication and sum, so that U is an element of W by definition. And then I'm just going to define Z to be Y minus U so that Y is equal to U plus Z. So the existence portion of the theorem is complete if I could try to convince you that Z belongs to W perp. So I need to show you that Z is orthogonal to everything in W. And while by the linearity of the inner product, it suffices to show that Z is orthogonal to each basis vector in beta. So that's what I'm going to do. So if you give me a vector in beta, you pick a j between 1 and k, let's just look at the inner product of z with that vector. Well, we said that z is y minus u, and then using the linearity of the inner product, I can split that apart. And then moreover, u, if I scroll back, you can still see the definition of it. U itself is a sum. So I'm going to put that in and use the linear product or the linearity of the inner product again. Okay, but over here in this expression, remember, this is an orthonormal basis. The inner product of vi and vj is 0 if I is not j, and it's equal to 1 if I is j. So of the k terms of that sum, only one of them survives when I is equal to j. So that sum just becomes y inner product vj times 1. Okay, well, y inner product vj minus itself is 0. So that shows that z is orthogonal to every basis vector in W, and hence by linearity, z would be orthogonal to everything in W. Okay, so that's what I'm writing down here. If you take any element of W, z will be orthogonal to it, so z is in W perp. So we've got existence. We've written our y as something in W plus something in W perp. Typical uniqueness proof, suppose that we've written y in two ways, say u plus z and u prime plus z prime, where the u's are in W and the z's are in W perp. Okay, so do a little bit of algebra, rearrange that equation. It means that u minus u prime would be the same as z prime minus z. And well, the u's are in W, so that difference is in W. It's a subspace. The z's are in W perp. It's also a subspace, so their difference is in the subspace. And if those elements are equal to each other, they must be in both of those subspaces. Okay, so I've got an element that's in both W and W perp. So if I look at the square of the length of u minus u prime, it's the inner product of it with itself. Well, if I just remember that u minus u prime is in W, but it's also in W perp, that inner product has to be 0. If that inner product is 0, then u minus u prime is the 0 vector. That is, u is equal to u prime. And then if that's the 0 vector, then z is equal to z prime. And I think that it's an important kind of thing to point out here that outside of the context of this, so that proves our theorem, that proves the uniqueness. And I think I would hang on to this fact that at the end of the proof, we just showed that if you have a vector that's in both W and W perp, it has to be 0. The W and W perp always intersect only in the 0 space. Okay, that's because the only way that a vector is orthogonal to itself is if it's the 0 vector, because otherwise the inner product of a vector with itself is the square of its length. For a non-zero vector, that would be a non-zero real number, positive real number. Cool. Borrowing the notation, I'm not going to restate it all. So in the notation of the theorem, we have a little corollary here that if you take any vector in W, take any vector in W and you look at the distance between it and that y in the theorem, that distance will be at least as big as the distance of y to u in the theorem. And the equality will hold if and only if x is equal to u. Okay, so another way to say that is that that u is the vector in W that's quote unquote closest to y, the given y. The distance between u and y is less than or equal to the distance between x and y for any other x in W. So it gives you a way of sort of locating a vector in this subspace that's nearest, smallest distance to your vector y. Let's take a look at the proof of that. So if we using the statement of the theorem to set the notation up, if I grab that x in W and I look at the square of the distance between y and x, well, y is certainly equal to u plus z. So I do a little bit of algebraic manipulation there. U and x are both elements of W, so their difference is an element of W, so it's perpendicular to z. So the Pythagorean theorem, it's an exercise. If two vectors are orthogonal, then the square of their length is the sum of the squares. The square of the length of their sum is the sum of the squares of their lengths. That's just the Pythagorean theorem. So that's true because u minus x is perpendicular to z. And then u minus x is some number that's greater than or equal to 0. So that sum is at least the length of z squared, but z is equal to y minus u. Right? So that gives the inequality, that the distance, because you can take the square root of both sides of that inequality chain. It tells me that the distance between y and x is at least the distance between y and u, the length of those vectors, that is. That's what I mean by distance. So there's the inequality. To get the last part of the statement, you get equality if and only if x is u. Well, certainly if x is u, then y minus x and y minus u are the same vectors, so they have the same length. Conversely, if y minus x is equal to y minus u, then looking at this chain up here, if those two numbers, the length of y minus x and the length of y minus u, are equal, then this inequality must have been an equality because the numbers on the extremes are equal. Okay, so if that thing is an equality there, then it actually means that this sum u minus x length squared plus length of z squared is equal to the length of z squared, right? Because of that inequality being an equality. Well, if that's true, you can subtract length of z squared from both sides to get the length of u minus x squared being 0, and hence u minus x must be the 0 vector, that is, u is equal to x. Cool. So what's a nice application of that? You've seen something like this, again, kind of in Calc 3. We can generalize this to higher dimensions, but let's just talk about R3 for a second. If you give me some plane in R3, two-dimensional subspace, and then you give me some point P in R3 that's, it can even be on the plane, but I drew it like it's there, then we can use that business above to find the distance from that point P to the plane W. You probably remember in Calc 3 working on an expression for this, how to calculate the distance from a point to a plane. Well, certainly the distance from the point to the plane should be the length of the vector or the line segment that you get by dropping a perpendicular, right, to that point. So that's what I'm indicating in my picture there. So that perpendicular I've labeled as the vector z. It's exactly the summand in the decomposition that we wrote above. If you take the vector u in w and add it to this vector z in w perp, then you get the vector y, right? So the distance from P to this plane W is just the length of that Z. It's the length of y minus u, where u was defined in the theorem above. And that is, if you take an orthonormal basis for W, you define u by letting it kind of have the Fourier coefficients, so the y's Fourier coefficients in that vector, in that orthonormal basis for W. Cool. You should play around with this. I think kind of, use a specific plane W, pick an orthonormal basis for it, and see if you can kind of recover that formula that you used in Calc 3. You can also think about how you could modify this to find, say, the distance from a point to a line, say in R2, and so on. Could be kind of fun exercises for you to do. That vector u in our theorem, it's called the orthogonal projection of y onto w. Maybe I could try to show you that picture while I'm saying that. Thinking about the plane w as being there, here's the origin of our vector space, and then I've got my vector y drawn there. And so the vector u, yeah, it's the sort of shadow of y. If you shine a light in the direction perpendicular to w, the vector u is the shadow of the vector y. It's exactly the projection vector of one vector onto the line through another in Calc 3, if you take W to be the some linear space. So the orthogonal projection of y onto W is just the component of that decomposition where you write the vector y as something in W plus something in W perp. Okay. Second and final theorem of this video lecture, ending our work in section 6.2, is this theorem 6.7. It has 3 parts. Each one of these is relatively straightforward to prove, but they're important results. So let's check it out. So let's suppose that we have some k vectors, v1 through vk. They're orthonormal, so they're pairwise orthogonal and have length 1. And it's a set of them in some n-dimensional inner product space V. Okay. So the first statement is that we can extend S to an orthonormal basis for the entire space V. Okay, so you'll notice that these first k vectors are the vectors that are in S. So we can sort of extend them to n minus k more vectors, making the whole thing an orthonormal basis. That's part A. Part B is if W is the name of the span of those vectors, then the ones that we extend with, vk plus 1 through vn, are an orthonormal basis for W perp. Okay. And kind of as a consequence of that, the dimension of V is the dimension of W plus the dimension of W perp for any subspace W of V. Okay, so let's see if we can't prove this. So looking at part A, we give ourselves this orthonormal set. Orthonormal sets are orthogonal sets with no zero vectors in them. So they're linearly independent. So the replacement theorem from way back at the beginning of our course says that we can extend that to a basis for V. So I've still got my first v1 through vk, but I'm calling the extended vectors wk plus 1 to wn, because what I'm going to do to that basis is just apply the Gram-Schmidt process to it. Gram-Schmidt process applied to any basis gives me an orthonormal basis. And this is an exercise earlier in the text, but since v1 to vk were pairwise orthogonal in length 1 anyway, when you Gram-Schmidt that basis S prime, you're not going to change the vectors v1 to vk. You're going to get exactly the same vectors that you started with. So you'll just change the tail end of it, the n minus k vectors at the end. That's an exercise 6.2.8. Okay, so that's how we produce this orthonormal basis beta. So that's the proof of part A. To prove part B, if I let, say, S lower 1 be the back half of that basis, vk plus 1 to vn, well, again, it's an orthonormal set, so it's linearly independent. And every vector in it is orthogonal to the first k vectors. So that set is a subset of W perp. So its span would be a subspace of W perp, because W perp itself is a subspace. So if you take any vector in W perp, we know we can write it as a linear combination of the entire basis using the Fourier coefficients. So that's a sum from 1 to n, right? But X is in W perp, so it's orthogonal to everything in W. So in particular, it's orthogonal to the first k vectors in this sum. So X dot, or X inner product VI for I between 1 and k is going to be 0. So this sum actually shortens. The first k terms are 0. So it's equal to the sum from k plus 1 to n of the same coefficients. And that, by definition, is an element of the span of S lower 1, of S sub 1. Yeah. So we've got a linearly independent subset that spans W perp. It's a basis for W perp, right? We already said that it's an orthonormal set, so it's an orthonormal basis for W perp. That's what part B said. And then finally, for part C, if you start with a subspace of V, well, it's also an inner product space under the same inner product, so you can choose an orthonormal basis for it. Start with a basis and Gram-Schmidt it, right? Use the work above in part A and part B to extend that to an orthonormal basis for all of V. And we can see that then the dimension of V, that's n in our space, would be the number of elements in this basis for W, that's k, plus the number of elements that we've extended, that's n minus k. Well, those things by part B are exactly bases for W and W perp. Cool, so that proves the theorem. Just as sort of a little bonus here, we didn't really, I left it to a video, talk about direct sum, but these spaces, W and W perp, like I commented earlier, they're always intersecting at 0. The only vector that's in a subspace and its perp space is the 0 vector. And the theorem that we just proved, I think here I mean theorem 6.7, I got the number wrong, is that, oh, no, excuse me, theorem 6.6 is the one that says every vector in V can be written as something in W plus something in W perp. So those two spaces together, their sum would be all of V. So if your sum is all of V and your intersection is 0, that's what we mean by this direct sum. Yeah, so it's another way of seeing that the dimension of W plus the dimension of W perp is the dimension of V. In fact, they're direct summons. So good. Okay, well, that's it for this lecture. Thanks for listening.